Let me start by thanking Kobe for inviting me to present my work. I guess it's always an interesting experience to present your own work in your own universities, right? Seeing the students sitting there as an audience who is going to challenge me, where it's supposed to be the other way around, right? I mean, and also good to see some of my colleagues here. So hopefully this talk, I guess, give us to share knowledge, to exchange ideas, and hopefully initiate more collaborations. And also, the topic is interesting, right? So when Kobe first invited me, I was just hoping to present a work that we recently did with, Professor Fiorenzo Ventrone. But fortunately, I mean, the schedule is actually rescheduled twice, which gave me more time to think about, okay, what would be the message that I want to deliver? And in the end, I was like, okay, I mean, maybe if I use a more gentle approach instead of presenting too much of heavy details, maybe it will facilitate the communication exchange. So I decided to change the topic a little bit. So here we are, and hopefully, I mean, the topic of ultra-fast computational imaging will give you some idea to think about, like how would the synergy of optics and computers could help material science. Okay, so for those of you who don't know what CEMDI is, I mean, I want to use the slides to I guess, advertise it again. So CEMDI stands for Computational Energy Material Design Infrastructure. Okay, so it's currently led by Professor Kobi Guma. So basically, it's a I guess a network thing that will bring together talents of different aspects from our institute with the common scheme of energy materials, right? So you'll find people who is doing computational energy material design. You'll find people like me who is mainly applying some computational reconstruction work for the material characterizations. So I mean, we also hope to basically create this network to bring not only the talents from our own institute, but also in Canada and globally, and also to facilitate a industry and academia partnership. So here is the link of the website. The website is beautiful, okay, and please go and check it out. So a little bit about me. So I mean, I'm from here, and I work in this building, and my lab is over there. My lab is called the Laboratory of Applied Computational Imaging, short for LACI. And we have basically two research missions. The first one is we use ultra-fast photonics and computational techniques to design new computational imaging systems. And the second research mission is we're going to use these designed systems for various of applications, ranging from materials to manufacturing and also for biomedicine. Okay. So in today's talk, I want to present you some general ideas of the following 5 questions. Okay. So the first one is, okay, why does material science needs optics? And in more particular, why does it need a single shot ultra-fast optical imaging? Okay. So after that, I want to talk about, okay, why single shot ultra-fast optical imaging need computers? Okay. So after we finish discussion of these two, I guess, backgrounds topics, and then I want to share you some knowledge about a specific example that embody the synergy of the imaging and computers. That is called compressed ultrafast photography, short for CUP. So I will, I guess, concentrate most of my time on the fourth topic, which is how can CUP help material science. And finally, I will have a very short summary to conclude my talk. Okay, so first question, okay, why, right? I mean, so to motivate the audience, I just want to say that, well, I mean, high-speed imaging is very cool. Okay, so I want to use this movie to start as an icebreaker. So this is a very classic or must-see Chinese movie called Kung Fu Hustle. And for those of you who come from China, you exactly know what I'm talking about. And for those of you who are interested, I'm proud to say that it's available on Netflix, okay? So in the movie, there's a very famous clip, okay? This big villain, this guy, can actually use his 2 fingers to catch a flying bullet, okay? After that, he left this very famous saying, and if we translate it into English, it says that in the world of Kung Fu, only speed at its utmost extreme cannot be defeated, okay? So, well, I mean, as an ultra-fast imaging guy, I generally notice this slow-mo clip, but after that, okay, what else can you get out of it, okay? So, as you know, I mean, we're living in this, I guess, 4-dimensional world, right, macroscopically. So we have 3 dimensions in space and 1 dimension in time. And if we only restrict ourselves in a classic world, so we forget about quantum stuff, then this 3D space and 1D time, they're really just independent, okay? So that means the work that we do to push the technical capability in the dimension of time usually have very little interference with the 3D space, okay? So that's why if you want to work on ultra-fast imaging and try to push the imaging speed, you usually can win a lot without losing anything, okay? And the second point I want to point out is that, for this very famous saying, it doesn't specify what kind of Kung Fu are they talking about, okay? So there are many of them. So, I mean, those actually give you some of the feeling that, okay, I mean, the speed is actually a very general, I guess, factor that can help for many different types of Kung Fus. And if you graph this idea to the optical imaging, that means that, okay, improving the imaging speed, okay, is generally a very plausible approach for pretty much all the image modalities, okay? So that was pretty cool, okay? I mean, but what would be the practical needs, right? So I mean, we actually want to use this slides to show that, yeah, I mean, for material science, there is an actual need for the single-shot ultra-fast optical imaging. The first reason is that many dynamics in material science, they're either non-repeatable or difficult to reproduce, okay? So some examples include, okay, phase change, right? So if you want to, say, shine a laser beam onto a piece of material and, well, they change from a crystallization to amorphous, right, phase. Well, after you finish this process, it's done, right? It cannot be returned. So this is considered to be a non-repeatable event. Another example is, for example, if I shine a laser beam onto a nanoparticle and it's melt, right? So once it's melted, it cannot be unmelt, right? So in this case, it's also considered to be either non-repeatable or difficult to reproduce. In this type of situations, right? So you imagine that you use a conventional imaging device that depends upon pump and probe, then it's not going to work, right? Because the event happens only just once. Right. So the second reason is that many conventional imaging modalities, right, have a limited accuracy and efficiency. What do I mean by that, right? So for many times, if you are looking for the good investigation of for example, whatever the material dynamics that you are looking at, you mainly have many parameters that you want to quantify. So if you only quantify 1 parameter per time, then usually this is not very efficient, especially if you want to quantify the time history of this particular parameter. So in this case, if you also rely on pump and probe based method, maybe the laser is not very stable, you have other perturbations in the experiment. So this would induce some unnecessary limited accuracy and efficiency. And finally, I want to remind everybody that, well, I mean, for material science, usually the dynamic is very fast and they are very small, okay? So in order to see something very small and also moving, we need high-speed imaging. So I'll give you an example, okay? So this figure shows the required spatial and temporal resolution for objects moving at different speeds. So as you can see that, well, if we just want to image something that's not very fast, say moving at 1 meter per second, and if the required spatial resolution is 1 micrometer, well, you need an imaging speed at 1 million frames per second. Okay, so in all those 3 scenarios, conventional pump and probe based method doesn't work or it's not very efficient. So in contrast, single shot ultrafast optical imaging is very attractive because in just one click, you'll be able to capture a movie that contains at least two spatial dimensions and one dimension in time. Okay, so after we know that, okay, there's a need, we need to see what's out there. Okay, so usually we can, I guess, categorize the existing technologies in single-shot ultrafast optical imaging in two areas. The first one, we call it active detection. Okay, so this one probes the transient event using specifically designed illumination characteristics. Okay, so I'll give you two examples. The first one is a 2014 very famous Nature Photonics paper, and this is called a STAMP camera. So what it does is first it chirp a femtosecond laser pulse and then chop it. So they break one probe pulse into 6 sub-pulses. Each one of them, they have a different color. So if you use this pulse train to probe the dynamic event, well, you encode the time into different colors, right? So at the detection side, you'll be able to separate them. Then this is how you figure out the time. And the one on the left is called a frame, okay? So instead of using different colors, we actually attach different sinusoidal patterns at different orientations to encode the temporal information. So even if everything is mixed up in the spatial domain, you'll be able to demix them in the spatial frequency domain. So active detection-based method has very high imaging speed. However, they have limited sequence steps, which means that, okay, how many frames you can get in the captured movie. For STAMP, we have 6, okay? So for a frame, we only have 4. So that means if you want to watch this material dynamics for a long time, it's generally impossible. And second, because we rely on the probe laser beam. So usually it says that, okay, if the dynamic scene emits the photon itself, or they're color selective, then you're out of hope. So to solve this problem, we can turn to the second category, which is called passive detection. Okay, so it means that, okay, instead of probing it using a femtosecond laser beam, we use the ultrafast detector to capture that. Okay, so there are also some examples, for example, in situ image storage CCD cameras or ultrafast framing cameras. So those things, because they're passive, they can be able to, they can image the self-luminescence or color selective transient scene. However, they also have limitations, which I will talk about in the next part of my presentation. Okay, so yeah, so I mean, why would single-shot ultra-fast optical imaging need computers? Well, let's follow our discussion from the previous sections here. So I'll talk about 2 general limitations. Okay, the first one is speed. Yeah, so probably everybody saw this before, right? It's the standard CCD or CMOS cameras that pretty much everybody used in the lab. So this one's from FLIR, and generally it can capture 100 frames per second. Okay, so what's the limitation? The limitation is actually at the interface. Okay, so you guys use, for example, USB 3 or Ethernet cable or GigE. So the output, right, is actually limited here. So even if you can take the image very fast, it cannot output fast enough. So this is the main reason why the imaging speed is limited. In order to overcome this, well, I mean, you can actually use a very fancy high-speed interface. So for example, this is a camera in our lab, which has a co-express cable, which can actually allow you to output the data faster. So in this way, you'll be able to improve the imaging speed from 100 frames per second to 5,000 frames per second. Well, however, at the moment, it's still limited by the interface, okay? So how to solve that? Well, people think that, well, I mean, let's just try to find a way to walk around, right? So here comes the example that I mentioned several slides ago, right? So it's called in situ image storage, ISIS sensor. So the design goes like, okay, I mean, now since the interface is a limitation, let's try to not output data, right? So they have one photodiode in the middle, and they have so many registers basically lying around. So if you capture some photons and you generate some photoelectrons, well, it will transfer it to the register and let it sit there, okay, during the entire image acquisition. So no data reads out until everything's finished. Well, in this way, you'll be able to push the limited imaging speed from 5K to 100 million frames per second. Is that fast enough? Well, I guess so, but it also have the limit, okay? So now the limit becomes, okay, I mean, we're against the physics now. So now, what's the limitation of this one in speed? Well, it is limited by the electron's traveling time because, okay, so the electron has to be generated and has to travel until it's read out. So this process usually takes 1 nanosecond, and this limits the theoretically maximum imaging speed of the ISS sensor to 1 billion frames per second. So 1 billion frames per second, if you think about it, okay, is this good or is it bad, right? So most of for many imaging applications, this is good, right? Because you're talking about a nanosecond temporal resolution. But is there any, sacrifice you have to make? Well, for this specific examples, yes. The first ones, you can see that, well, the fill factor for this design is very, very small because you have to leave lots of space for the charges to be registered, right? So that means the sensitivity of ISS sensors usually reduced. And at the same time, well, we'll look at the 1 nanosecond imaging speed. For the speed of light, right, so you still traveled at the meters level. So, I mean, if you really want to freeze the motion of the light, then 1 billion frames per second is still considered to be not enough. So the next limitation I want to discuss here is about dimensionality. Okay, so here what I'm showing here is the working principle of a streak camera. So I will spare you with all these technical details, but just trying to say that, well, I mean, for streak cameras, it uses a very specific optoelectronic method to convert time like this into space, okay? So this is why if I'm using the streak camera to see a light pattern like this, right? So INRS, 4 letters, each one occupies a different spatial and temporal position. This would be what I would see in the internal image sensor. So one axis is still used to display space, but the other axis is now have to be display time, right? So in the conventional setting, streak camera is considered to be a ultra-fast electronic device with the imaging speed of 10 trillion frames per second, right? Now we're talking about 100 femtosecond type of temporal resolution. But because it can only be imaged through a line, so it's usually considered to be 1D imaging only. So it has a limitation in dimensionality. So it seems that, okay, for hardwares in the ultra-fast imaging speed, in ultra-fast imaging, we have limitations in speed, we have limitations in dimensionality. Seems that we're running into a dead end. So what to do, right? So this is when computer comes to rescue you. And in the context of today's presentation, I just want to mention one very popularly used computational imaging scheme called compressed sensing. So what is compressive sensing, right? So compressive sensing is built upon a concept called sparsity. Sparsity is what? So which means that if you have a, matrix 1D, 2D, 3D, or 4D, if there's lots of elements in this matrix has a 0 value, then generally we can call this matrix sparse. And fortunately, for pretty much all the scenes that we're trying to see, they are sparse. So here's an example, right? So this is a very famous, image that you guys seen in MATLAB, right? So this is a cameraman. So you can see that for this man's hair and coat, right? They're black, which means that most of the element, they have 0 intensity. That means that, well, they don't contain information. So if you sample them or if you don't sample them, that's okay, right? Because you don't lose any information. So compressive sensing theory is actually built upon this sparsity. And it says that, well, in this scenario, the required number of measurement M can be way smaller than the number of unknown N. So you can first compressively record the data and then use a computer to do the image reconstruction and have a very good, reconstruction quality of the data. So by combining the existing hardware of single-shot optical imaging and the computer, right? I mean, we can actually do a lot of things about it. So I mean, here I would like to present you a very nice example in this category called compressed ultrafast photography, CUP. How does it work? Okay, CUP is a coated aperture optical imaging system, right? So usually it has 2 general steps. So the first one is if you have basically a movie, right? So which is showing us IXYT, right? XY is a spatial dimension, T is time. And you use a physical data acquisition to record it, okay? So there's 3 steps. The first one is we need to do encoding, okay? So literally, it means that you put a mask there, right? So random mask and let the light transmit through. So in this way, you basically punch a lot of holes into this 3-dimensional data cube. And later on, you do sharing. So I mean, if it first like this and then becomes like this. And finally, you do a compression, right? So that means, okay, so using these 3 operators, you will be compressively record a 3-dimensional data cube into a 2D snapshot, literally just the image. However, this is only half of the story because you have to take it into the computer to do image reconstruction. So there are many different ways to do this, but I mean, in general, they're either analytical-based method or basically machine learning, right? So analytical-based method that relies on you have the knowledge of the physics model, right? And then you put it in and trying to solve the minimization problem. Or you can basically put the data into a well-trained, say, deep neural network, and which also works. So both, either way, it will give you the movie, okay, the movie. Now, I want to basically use the slides to provide an additional analogy. So hopefully we're all on the same page. So the image on the top shows a very typical setup of cup. And so how can we understand this thing? So, you know, I mean, I want to use, for example, the shopping experience that you guys all have in the supermarket. So imagine that, you know, this dynamic scene can be regarded as the 3 bottles of milk, okay? And so, I mean, when you want to do spatial encoding, you know, then this means that you are actually putting some barcodes on this on these bottles of milk, right? So, well, I mean, maybe they look identical in the beginning, but after you put the barcode, you know which one's which, okay? So then the sharing unit and integration can be regarded as how you purchase them, right? Let's say I want to buy 3 bottles of milk and put them into the shopping cart. So at that time, you know, this is basically lumped measurement, right? I don't know which one's which. So how to do that? Well, this computer reconstruction can be generally regarded as a checkout process. So you go to a checkout, then what the cashier do? He or she will actually use a scanner to scan the barcode so they know which one's which. And after that, you know, you get 3 bottles of milk. So I hope this is, I don't know. I mean, I hope this analogy is good enough for you to kind of like at least have some sort of general idea about how this works. Okay. The cup technique was invented back in 2014 when I was a postdoc. So I mean, this is the first prototype where we built the hardware of compressive sensing with the streak camera, so that we overcome the dimensionality limitation in the streak camera. So that means the streak camera can still image at a very high imaging speed, but instead of doing 1D imaging, now we can do 2D imaging. Okay, so then, you know, we use another, you know, 2-3 years to improve this thing, so that in 2017 we reported the lossless encoding cup. But I mean, the imaging speed is still 100 billion frames per second. Okay, back in 2018, you know, we upgraded the system so that it actually produced a system that still holds the record of receive-only single-shot ultra-high-speed camera with an imaging speed of 10 trillion frames per second. So CUP as a light-speed camera has been used in many, many different scientific discoveries. So I want to share some, I guess, real-time movie that captured over, you know, last few years. The first one is, okay, so light-speed camera should be used to see light. Okay, so now with the imaging speed up to 10 trillion frames per second, we can really, like literally, like freeze the light motion. So the first movie shows the, you know, the light refraction at the air-resin interface. I guess the analogy can be drawn as, for example, if you have a straw you put into a, you know, transparent glass with half water, half empty, then you see the straw actually bent. So this is exactly the same thing as what we're seeing. And this one shows the spatial focusing of a 7 picosecond laser beam imaged at 2.5 trillion frames per second. And this one is done by my student, Yiming, where we show the sequential arrival of two spatially modulated femtosecond laser beam at 500 billion frames per second. And it has also enabled many different new applications. For example, this one shows the phase contrast count of a propagating shock wave generated in water. And this one shows the first capture of photonic Mach cone, which is the analogy of a sonic boom. Okay, so and finally, we can also see the spatially resolved fluorescence lifetime imaging. So then this brings me to the central topic of today. Well, I mean, how would CUP help material science, right? So, well, I mean, CUP is a light speed camera. So, I mean, there are many, many different dynamic scenes in the material science that is either non-repeatable or difficult to reproduce, right? So the CUP can definitely help as a characteristic tools. So here I would like to use the 3 examples to show what I have been done and what we're working, and a little bit projection to the future. The first one is called the stereo polarimetric CUP, okay, so called SP CUP, which I published in 2020 as, I guess, the last postdoc project, okay? So I will spare all the technical details, but I mean, you could just think about this thing as a high-speed camera that can see the dynamic event that represent in the polarization and also in 3D, so X, Y, and Z. So the demonstration here shows the evaluation of the polarization dynamics of a pulse that's propagating in the scattering media in 3D. So as an application, we use it to image the early stage plasma emission. And here shows the schematic. Okay, so we have a femtosecond laser pulse, and we focus it on a silicon wafer. Okay, so generate the plasma. So the light will be collected by the objective lens, pass through some filters and the tube lens, and interface it with the SP CUP system. So here shows the movie. So this movie shows the real-time imaging of expanding plasma plume. And the image on the left shows the intensity dynamics, and the image on the right shows the polarization dynamics. Okay, so I mean, this is a 2D color map. And the vertical ones is basically showing the averaged linear polarization angle, and the color shows the degree of linear polarization. So these movies actually provide provide a rich information that we can analyze. So first is we can analyze the speed, I guess, distribution over angle. And in this case, we found out that, yeah, I mean, it's actually pretty uniform. And then we actually thought about, okay, I mean, what would be the polarization dynamics change in the initial phase of the plasma? We found out that, well, actually the degree of linear polarization drops in the first 1,000 picosecond, while the averaged angle, well, the linear polarization angle stays constant. So, I mean, our explanation is basically suggests that, okay, I mean, this is due to the homogeneous decreasing of anisotropic electron distribution function over time. Okay, so we don't know that, but I mean, this is just our prediction. So, I mean, this is basically want to show that we have the capability to provide the analysis of the material dynamics over multiple photon tags. So the second one is our recent work with Professor Fiorenzo Ventran by using the CUP technique to image the phospholuminescence intensity decay of upconverting nanoparticles. So this work is done by my PhD student, Jinyang Liang. So back in 2019, we actually came up with this idea to generate this, what we call it like economical version of CUP. Okay, so the working principle is still the same, but instead of using a very fancy and expensive street camera, we actually built it a rotating mirror street camera by ourselves. So the idea is, okay, I mean, we want to target the imaging speed that's much slower, but we want to solve the limitation in speed in most scientific cameras. So the most, I guess, perhaps the biggest advantage is that, okay, I mean, this system is suitable for pretty much all the CMOS or CCD cameras. So I talked about this in the previous slide, saying like, okay, I mean, well, these cameras, they may have very nice technical advantages, right? So maybe it's very sensitive, right? Or maybe it can sense IR or mid-IR photons, but usually these cameras, they're very slow. So we want to keep these advantages. And while by adding these optical elements, we bring in the ultra high speed imaging capability to these cameras. Okay, so we have been using this thing to see many different dynamics. So this one shows how a microsecond laser pulse train passed through the transparent. And this one shows the imaging of a fast moving ball pattern at 140,000 frames per second. And for this system, yeah, I mean, we're also collaborating with many different people to trying to improve its performance from the software perspective. So this one's done with a collaboration of our own Tiago Falk. So we basically use the snapshot to video auto encoder to improve the imaging speed. So compared to the existing ones, as you can see that the image reconstruct the image quality and also the quantification of the the centroid are much better. So more recent work is also done with the collaboration of Professor Henry Aguirre in Colombia. So there we further improve the capability of deep learning neural network. So we want to change the concept that a deep neural network is only a substitute of the existing software. But we're saying like, okay, I mean, using this deep high-dimensional adaptive net would be not only reconstruct the image, but we can also improve or optimize the encoded mask and also figure out the actual sharing function. So we use the software to provide the feedback to the hardware. So with all this development, now it's about application. So I mean, this is also done by my student Jinyang Liang and also Artyom from Fiorenzo's lab. So by putting everything together, we engineered a new concept or a new image modality called split, okay, single shot photoluminescence lifetime imaging thermometry. So we basically use this system to, I guess, probe the upconverting nanoparticles. And here we use a very conventional one, sodium gadolinium tetrafluoride is a core shell structure. Okay, so we use the 980 pulsed laser to excite it over a wide field. And then the emission generally contains two bands. So either we focus on the green one or we focus on the red one. So we select that by using a filter. So after that, we basically use this high sensitive electron multiplying or EMCCD camera to record the photoluminescence intensity decay with very high sensitivity. Okay, so this is basically how the system is working. So after that, we have two views and we put it in computer to do image reconstruction. So if you look at the model, well, I mean, they're pretty much the same as what I just talked about, right? So the forward model is really, one is doing a direct temporal integration. The other one is doing basically a cup measurement. So after that, we put the recorded data into a PMP ADMM network, which has a better image reconstruction capability because it basically breaks the overall minimization problem into multiple small ones. And each one of them, you have more parameters to control. So generally, you have a better capability to get a good result. So if you get a good result in individual ones, well, overall, you can also get a good result. So the reconstructed movie has 100 frames. Each one of them has 460 times 460 XY pixels. And we tune the imaging speed to be 33,000 frames per second to match the lifetime of the nanoparticles that we're using. So finally, because the emission is Boltzmann coupled, we can actually use the captured movie to figure out a 2D temperature distribution in a single shot using this equation. So now, let me show you some experimental result. Okay, so As a proof of concept demonstration, we first quantified some of the technical specifications, spatial resolution, field of view, sensitivity, and then we covered 3 types of nanoparticles with different transparencies. And these nanoparticles, they have the same core, but have different shell thickness. So the one with the C is the thinnest, the one with the N is the thickest. Okay, so if you look at the captured movie, then you can see that C definitely has the highest or fastest decay compared to N, which has the slowest. So this means that, well, I mean, they have different lifetime, and we can plot the average intensity over time here to figure out, well, the average lifetimes of C and A and N, they're different, which makes sense because, I mean, if the shell is very thin, then it definitely does not have that much good protection. So, you know, the excited electrons, they want to come down to the ground state. So this basically explains. And please don't forget that since we're talking about a wide field lifetime mapping device, we'll be able to get the lifetime from every single point of the field of view, and then we'll be able to plot the statistics. So the second experiment is, okay, I mean, we try to change the temperature of these nanoparticles from 20 degrees Celsius to 46 degrees Celsius and try to watch how would the intensity decay change. Okay, here's the movie. Well, it doesn't show that much, but I mean, if you use color to encode them, then you can definitely see that, well, I mean, for both the green and the red upconvergent emission, the lifetime decreases when the temperature increases. So this allows us to establish a lookup table to link the temperature and the lifetime. Okay, and then we did a longitudinal temperature monitoring by putting the nanoparticle underneath a chicken tissue phantom, and we monitored that for over 4 hours. Okay, so this shows that the measured temperature has a very good agreement with the preset ones. So as an application, we labeled a single layer onion cell sample with these upconverting nanoparticles. And we moved the sample underneath the field of view at about 1.2 millimeter per second. And we use a split system to capture the lifetime indicated temperature map at 20 frames per second. So here's the movie. So yeah, it shows that, yeah, I mean, we'll be able to, for the first time, you know, watch a dynamic lifetime indicated temperature movie, right, of the upconverting nanoparticles. In order to demonstrate that the lifetime-based method has a better accuracy compared to the intensity-based counterpart, we selected 4 regions in the intensity-based map, okay? So if you show that here, then you see that, okay, these 4 regions, they have different intensities. If they use the intensity-based method, you would have already concluded that they have different temperatures. However, this is not the same as what we have set up in the experiment. But if you look at the lifetime, then yeah, I mean, they all pretty much have the same thing. So this confirms that the intensity-based method is not as accurate as the lifetime ones. And moreover, we actually tracked the time history of the intensity of all these 4 regions. And you can see that from this figure that they have different trends. So for example, the yellow one, that goes down. The magenta ones, it goes up. And these 2, they're pretty much stay the same. So once again, if you use intensity-based measurement, the data would, I guess, confuse you. But if you look at the lifetime determine the temperature, yeah, they actually have remained constant, right? So the fluctuation is plus minus 0.35 degrees Celsius, which is actually very good. So finally, let me talk about a little bit, I guess, future work or the work that we have been doing. So once again, this is Jinyang Liang's work, and the idea is very simple. Okay, we want to use, you know, cup with TEM because, I mean, here in our center, we have probably one of the best, right? I mean, TEM infrastructures, not only in Canada, pretty much all around the world. For cup, right? I mean, right now, what I just said, everything's about optics. So in that case, you know, the spatial resolution is naturally restricted by the diffraction limit. And unfortunately, for the material dynamics, they're very fast and they're very small. So how are we going to see both picosecond or femtosecond dynamics at a nanometer spatial resolution? This is basically the driven motivation behind this project. Okay, so when I started here, I collaborated with Professor Acheng Yutsever to basically see, okay, I mean, is there any possibility that we can model this? So this is basically the proposed imaging modality. And Xianglei did some optimization work and simulated the, I guess, simulated the images that are taken from the actual TEM setups, right? So this one, well, if I play the movie again, this one shows the dipole intensity of silver nanoparticles. And this one shows the movement of a cantilever of the field-to-field. So now we see that, yeah, I mean, there is actually hope to actually use the cup with the TEM. Now, right, we're collaborating with Professor Kenneth Meiling, and you know, the work is currently leading by our postdoc Samik. So now we're being serious. Okay, so we want to build it, and we found out that the movie mode, dynamic TEM here at NRS is actually a perfect platform for us to implement this idea. So we just need a very minimal change of the existing tools in order to incorporate the cup modality into the facility. So we are doing something with the aperture right here. You know, instead of just having a round aperture, we want to have a coated aperture. So this is a very, you know, very new result. So now we can see that, well, I mean, we are able to fabricate the whole patterns by using the fib milling. So, I mean, it sounds an easy job, but I mean, there's a lot of tricks to be figured out before we actually get here. And then we also did some work with the deflector. Okay, so instead of having this step function, we actually have a linear ramp. So this one shows that we can actually have a very good linearity in both, I guess, shear left and shear right. So that means we're very close to putting together a system and to do the actual measurement. So I really hope that you know, yeah, I mean, we'll get to the see the light out of the tunnel very soon. So let me summarize. Okay, so the development of the compressed ultrafast photography systems in IRS actually has been, I guess, has generated lots of different, I guess, I would say very encouraging outcomes. So far, we can do multi-scale imaging. So we have systems that has the imaging speed from millions frames per second all the way to billion frames per second. And we can see big and we can see small. So right now we're working with Professor François Legalet to hopefully push to a system that has the imaging speed more than 100 trillion frames per second. At the same time, we want to also minimize the size of the cup system so that hopefully one day it can be fit in a cell phone. So this will target the consumer product. And at the same time, we have demonstrated the multi-wavelength imaging. So the data that I showed you just now contains the imaging from UV to visible to near infrared. Right now, we have an ongoing collaboration with Synchrotron Soleil, where they use the cup imaging to see X-ray. And I just talked about the electron imaging. So that's basically a CUTM. And we're also having some project that hopefully we can extend this modality to mid-infrared. And finally, we're also working on multi-contrast imaging. So most of the data that I showed today contains intensity, but I mean, cup can be easily combined with other image modality to realize, you know, sensing of other contrasts, for example, refractive index of phase, or maybe even polarization. In terms of application, so we finished the rare earth nanoparticle characterization of up conversion. Okay, right now my student Miao is working on the same product, but she wants to see the IR to IR conversion. So I mean, she's working on Stokes emission. So regarding the lifetime-based thermometry, we demonstrate the biological tissue and cells. But right now, my student Yingming and Miao, they're working with our colleagues at the University of Montreal to implement the system for skin cancer diagnosis and treatment. So the second part that I talk about today is about the plasma. Okay, so I mean the ongoing work is we want to use to use the plasma imaging capability that we have to see the lips, right? So the laser-induced breakdown of agricultural materials, and this work will be I guess conducted by my new PhD student Madhu, who just got here a few weeks ago. And finally, we want to push the limit of the speed. Okay, so my postdoc Jinyang is working on another project where we actually demonstrate that we can actually have a real-time imaging with a femtosecond temporal resolution for two very important types of materials. So we actually saw the phase transition of the magneto-optical materials and also semiconductors. So finally, let me wrap up the thing by saying that, okay, what we are doing here is actually an optical pursuit of Olympic symbols. So everybody knows that, okay, I mean, Olympics slogan, right, has 4 words. Well, used to be 3, and they add another one. Okay, I think this is a very important one. So now for Olympics, right, you always say it's faster, higher, stronger, and all together. So how can we draw the link between the Olympic symbols to the optical imaging of the advanced material characterization? We want a faster, what we want a faster imaging and sensing. We want a higher spatial and temporal resolution, and also want a stronger data acquisition and processing capability. But last but not least, we want to have a synergy, okay, between the optics and computers, because I believe that the knowledge and expertise from both fields, they can actually be well joined together to solve the limitations in both fields. So I mean, this is like a win-win-win-win-win type of situation where you overcome the technical difficulties in the existing system, which in turn will give you more capability to see many material dynamics that is not possible before. Okay, so hopefully in today's talk, I've convinced you that the synergy of optics and computers can help CEMDI. So my credit goes to my student. I mean, that's, they're the one who, sit in the lab and do all the hard works. And finally, the credit goes to the funding agency that supports my work. So I wrap it up here. Thank you very much. I'll be happy to take questions.
Wonderful talk.
Thank you.
The floor is open for questions.
Yes.
Now, have you observed something really surprising, something new in physics with your imaging system?
Well, that's an interesting question. I think I guess I would spin this question around to one of my favorite projects. Okay, so I think for now, I think I enjoy the most about that image of the photonic Marcon. Okay, so because that is actually predicted to be true because, but I mean, it's somebody, I mean, nobody actually thought about in this direction because, so if you draw the analogy between the photonic Marcon and sonic boom is like supersonic, right? So if you draw the analogy, that means we need a superluminal material. So how to achieve that? Well, I mean, lots of people say that it's not possible because Einstein, right? So then we actually realized that we can achieve a superluminal, which is faster than light speed in the material. So this links to, for example, Cherenkov radiation, and all these like relatively bizarre optical phenomena, which is very difficult to achieve. So what we actually find out is actually we could play around with 2 different materials that have different refractive index. So one has smaller one, the other one has a larger one. So if you look at the scattered photons from the what we call it tunnel, which has a smaller refractive index, that can be regarded as a superluminal light source compared to the display panel that we have. So I mean, then the result works beautifully, and yeah, I mean, I didn't expect that I could get this kind of result. So I mean, that's something that I found very exciting. Yeah. So but I believe that I mean, the second part of my answer to your question is that you never know, right? And so I think for the project that we're working on right now, I think the CUTM is something that excites me the most because I mean, it's always nice. Well, I think for all of you, I mean, here, if you look at Professor Federico Jose's lab is nano femto, right? So I mean, I think nano femto really makes sense because you want to see something super, super fast, and you want to see them in a very, very small spatial scales. So I think the CUTM work really has the capability to see that. I hope that we'll be able to see something that will blow my mind. Yes.
So, nice talk to you.
Thank you.
So I have one question for your nanoparticle lifetime imaging, right? So what was the spot size when you excite your nanoparticle? So how many nanoparticles you need to excite? Is it ensemble of nanoparticles or few nanoparticles?
Okay, so the spot size is actually, well, I mean, we're not doing focusing. Okay, so this is a wide field excitation. So if I go back, I don't know, maybe 35, let's see, 25. Yeah. So here, if you see, well, I mean, this is basically the beamline for the excitation. Okay, so we have the laser, and we actually use this lens so that the wide laser beam is actually focused at the back aperture of the objective lens. So then that means that it will deliver a wide field illumination. So there's no spot size, but we basically excite everything. So now about your question about the nanoparticles. Yeah, we definitely, we cannot actually see like individual nanoparticles. So they have to be a group. And I don't have the number for you about I guess, the number of nanoparticles that we can see. But I mean, we quantify the sensitivity using the minimum light level that we can actually see the signal. But if you're interested, I mean, I will be able to find the number for you because it's in somewhere in the supplementary of that paper. So,
okay, the second question. So if you want to do it like for semiconductor, so it can be thin film or nanowires or nanocolumns, anything, or it has to be nanostructures.
Right. So, well, nanowires, I think it may be challenging because nanowires is definitely, I think, smaller than the optical diffraction limit. So, I mean, if the nanowires is hundreds of nanometers, I think it's good, right? But other than that, we may have to think about way to combine this thing with a super resolution microscopy. It can be challenging. Yeah.
Ensemble of nanowires. So
yeah.
Like forest of nanowires.
Right. Yeah. Once again, if you just want to see the signal without seeing individual nanowire structures, I think this thing can definitely help you. Yeah.
This is the only time we'll ask the question.
Right. Please challenge me. Okay. Yeah. Yes. Well, sensing, can you be more specific? What do you want to sense? Anything? Right. Yeah, well, I mean, then that means CUP to really use with its full potentials, okay? You want to find something that's transient, okay? So basically, you know, for this particular project, okay, we're actually trying to link the transient light intensity decay to the temperature. Okay, so basically we have a lifetime, and if lifetime is high, we think the temperature is low. Okay, but the lifetime is low, then we think temperature is high. So this is how we link the lifetime and the temperature. And then we use the temperature as a biomarker to indicate the abnormal metabolism in, say, cancer region. So this is how we draw the link. So, I mean, if you want to, for example, sense, I don't know, like say the leakage of some dangerous gas, for example, that are flowing around, then I guess you can directly use this thing with a spectroscopy. So maybe you have some abnormal, I don't know, either drop or increase in the spectroscopy, spectroscopic imaging over a short period of time. So this is how you can detect it. So I would say that the temperature or any other things that you want to sense has to be linked with optical signal. So the optical signal in this context has to be transient, okay? So I guess I hope I answered your question. Yeah.
And is it possible to control the size of the pump laser somehow in detail?
The size of the pump laser in detail.
If you want to excite some specific region for in terms of specific region of nanoparticles, is it possible to control the?
Well, okay, so the pump laser, do you mean the pump laser, like pump optics laser, or I mean the, well, I guess the answer for your first question, if I understand you correctly, it's possible, but it may not be relevant to what you want to do, okay? So, well, Samik will be able to answer this question with more details, but I mean, what I understand is the pump laser goes to the photon emission, okay? So there you produce a pulse of electrons, where then you basically focus them onto your sample. So, you know, if you have a sample there, then you have to tune your, I guess, electro-optic lenses to control the excitation area. But I mean, for the laser that you're using, it's used to basically generate the electrons. So I think there's a subtle difference between the two. Yes.
Well, first I want to acknowledge the impressive work that
Thank you.
impressive.
Thank you.
I've been following what you do in the papers, but like seeing all together combined, bravo.
Thank you.
So, and then I've more of a curiosity. So the two-time project that I'm very, very interested in is closer to quantum, knowing more about materials. So do you have any idea about the electron fluence when you use your Q10, like with respect to a normal 10, do you try more material with the electrons or different?
I would think that, well, first of all, I don't, I would, yeah, I mean, so first of all, I don't have the specific number to answer your question, okay? But if I understand you correctly, I think we're not frying that much, okay? Here's why. Let's see, maybe, oops, sorry. So let's see, if I can go back to that slides. Okay, so here's the thing. First of all, you know, since we're working with the DTAM, right, the platform, so we're talking about a, I guess, relatively big illumination. So we're not trying to focus on anything, but we have a like wide field illumination beam. At the same time, you know, one of the, I guess, motivation for doing the QTAM project is that we don't want packed so many electrons all together because yeah, because previously that's basically how let's say UTAM did, right? But so if you pack lots of them together, you generate a very short electron pulse, and that defines the temporal resolution. But if you packed so many things together, I mean, the electrons, they'll have them basically repel from each other. So in the end, you will have the distortion in the temporal domain. So here, what we want to do is instead of doing it, you know, basically pulse by pulse, we have a very long pulse. So the electron density is not that high. So in this way, we hope that, okay, we pack the same amount of electrons, but, you know, it's longer. So in this way, if you think about the intensity towards this, the sample is actually less. Yeah, so so I think this is my my answer. Yeah. Hmm. Yeah. Right. Yeah. Okay. Good to know that. Yeah. I mean, we probably should talk more when this thing is ready. Yeah.
One quick question.
Yes.
So what kind of advancements you need from the computational side? What you are using currently, what module algorithm you're using in deep learning or neural nets? And do you think there is a room for improvement there?
Oh yeah, definitely, definitely. So okay, so I can share a bit more details about, for example, the reconstruction we are actually using. So I mean, typically you have two. Okay, so the first one is we call the analytical based method. I mean, there, I mean, you basically have to rely on the iteration. Okay, so hundreds of iterations. So I mean, if you ask my student, they will probably tell you that they sit in front of computer for the entire day and just trying to wait for the result. Okay. But I mean, this thing is also good because we can have more control. So basically, you know, like if the mask that we're using is not exactly binary, I mean, we can take this into consideration, but it's also slow. For this one, you know, DNN, well, it's fast, right? So basically we can do a real time, but the challenge for this one is it's scene dependent, right? So I mean, if let's say we want to image something that's moving around in the space with a static background, we're ready to train the neural network in this way. But later on, if we just want to have a static image that just have an intensity change, then we may want to do something else, right? So actually, you know, if you want me to ask my wish list, it would be like a universal model that can be applied for many different types of ultra-fast scene, right? So for that, I think right now, maybe because they're also talking about, for example, deep unfolding. So where you want to join these two types of schemes together. But for that, well, I mean, we just don't have that much expertise. So maybe, I mean, you could help us to design this thing and train the yeah. So.
Another quick question. I'm just wondering, what is the smallest and what is the biggest thing you have imaged so far?
Okay, biggest thing. Okay, so it's funny. Okay, I didn't put it here, but I mean, in the early days, after we invent this, you know, cup camera, we actually want to apply that to lidar. Okay, so basically the one that you see, you know, Google, you know, all the other things. So instead of, you know, having a beam that's, you know, moving around, we actually shine a laser beam and trying to capture the backscattered photons. So I guess the largest you know, object that I image is basically a gold comic fish that's moving around, and then, you know, we're trying to treat the fish so badly. So I mean, we're saying like, okay, clear water, no problem. Okay, how much mud do I need to add? So I put some mud. And later on, well, mud is not good, and we pour some milk. So I mean, to try to increase the scattering, so that makes everything challenging. Okay, because in the area of lidar, I think seeing through fog is something that everybody is trying to achieve. The smallest thing is probably just the one that I showed, right? So now we have the capability to resolve, I guess 10 to 20 micrometer size object. So I mean, you can see the skeleton of the onion cells. So that's probably the smallest thing that I've ever seen using using cup cameras.
That's very impressive work. Do you think soon we will have them cheaper and easily accessible on the phone, these cups?
Yeah, so I mean, yeah, I mean, they are available in the lab right now. I mean, we have a few, I guess, project which aims to kind of like reduce the size and try to make it a compact one box device. So yeah, so I think you know, several of my students are working on that. Yeah, I mean, it's definitely one of the goals to kind of like have this, you know, small compact product which can be used as a general tools for material characterization, and hopefully one day it will be combined with a cell phone. Yeah. Yeah.
That's such a fantastic work.
Thank you.
Again, let's thank our speaker.
Thanks, guys.